Hello, my name is AYFER from the Department of Electrical and Electronics Engineering at İzmir Katip Çelebi University. In this video, I will be presenting LABFLOW, an IoT-based real-time laboratory occupancy monitoring system developed for Fundamentals of Internet of Things course. The photo you see on the right is the actual hardware prototype I built, an ESP32 microcontroller connected to infrared sensors and LED indicators on a breadboard. This system uses infrared sensors, beam sensors, and ESP32 and the MQTT protocol to deliver real-time occupancy data through a web-based dashboard. I will now walk you through the problem, the system design, and the live demonstration. Let me start why LabFlow was needed. In most academic institutions, laboratory spaces are shared by many students. The most common way to check if a lab is available is to physically walk there and look. This is inefficient, time-consuming, and unreliable, especially in large buildings. Other solutions exist, but each has serious drawbacks. Camera-based systems can achieve high accuracy, but they raise serious privacy concerns and require heavy computational resources. Multi-sensor and machine learning approaches improve accuracy, but they significantly increase cost and deployment complexity. And the result? Students have no real-time remote visibility into lab status whatsoever. LabFlow addresses all of these at once. A low-cost, privacy-preserving IoT-based solution using infrared sensors, ESP32, and MQTT for real-time lab occupancy monitoring. LabFlow follows a three-layer IoT architecture. The first layer is the sensing layer. Two infrared beam sensors are placed at the laboratory entrance. An ESP32 microcontroller processes the sensor signals using a state machine to classify each beam interruption as either an entry or an exit event. The second layer is the communication layer. Once the ESP32 determines an occupancy event, it publishes the data to a Mosquito MQTT broker over Wi-Fi. MQTT's publish-subscribe model ensures lightweight, low-latency delivery. The broker runs on standard port 1883 and uses a WebSocket bridge on port 8083 for the browser dashboard. The third layer is the application layer. The web dashboard subscribes to the broker via WebSocket and updates in real time, showing the current occupancy count, a capacity utilization bar, the status classification, and the live event log. This three-layer design ensures that each component is independently scalable and replaceable. Let me go now into more detail about the hardware. The photo on the left shows the actual prototype. The system consists of an ESP32 microcontroller on a breadboard, connected to two infrared beam sensors and three LED indicators. The ESP32 is a Wi-Fi enabled microcontroller that handles all signal processing, occupancy counting, and MQTT publishing in a real time. Infrared sensor A, which is a sensor 1, is on the entry side of the doorway. When it is triggered before sensor 2, the system classifies the event as an entry and increments the count. Infrared sensor B, which is the sensor 2, is on the exit side. When it triggers before sensor 1, the event is classified as an exit and the count decreases. The three LED indicators, green for free, amber for critical, and red for full, mirrors the current system status in real time alongside the dashboard. The logic at the bottom of the slide summarizes it clearly. S1 triggers first, then S2 means entry. S2 triggers first, then S1 means exit. Now the communication layer. The data flow is simple. The ESP32 publishes to the Mosquito broker and the web dashboard subscribes to receive updates instantly. Each MQTT message carries a JSON formatted payload with 4 fields: the current occupancy count, the status classification, the event type, entry or exit, and the timestamp. For example, the payload shown here, count is 8, status is critical, event is entry. This means the 8th person just entered the laboratory. MQTT was chosen for 4 key reasons. First, it is extremely lightweight with minimal bandwidth, perfect for an embedded device like the ESP32. Second, the publish-subscribe model allows one publisher to serve many subscribers simultaneously. Third, it supports quality of service levels for guaranteed message delivery. And fourth, the WebSocket bridge on the port 8083 allows the browser dashboard to receive live data natively without any additional middleware. Now, I will show you the complete system working in practice. On the left, you can see the pink foam doorway prototype with the two infrared sensors mounted on each side, and the LABFLOW dashboard running on the laptop screen behind it, currently showing a free state with a count of 1. I will now play the demonstration video. This is the hardware prototype. You can see the ESP32 microcontroller mounted in the center of the breadboard. On the left side, the three LED indicators are visible, red, yellow, and green, which will light up to reflect the occupancy status in real time through this demonstration. The breadboard is connected to the infrared sensors via jumper cables. The yellow and green LEDs indicate the system is powered on and in free state, meaning the occupancy is currently 0. Here you can see the ESP32 module more clearly. It is connected via USB to the laptop for power and communicates over Wi-Fi with the Mosquito MQTT broker running on the same machine. This is the doorway prototype, built from a foam board. The label on the right reads Enter, indicating the direction of entry. The two black cylinders mounted on each side are the infrared beam transmitters and receivers. One is sensor 1, which is on the entry side, and the other is sensor 2 on the exit side. Here you can see the sensors clearly. The label is 2T Mark Sensor 2 transmitter on the 4 wall. The system is running and sensors are operational. Based on the testing you just saw, here are the key performance results. Detection accuracy was high. Under normal operating conditions, including single person and consecutive movements, the system correctly classified every entry and exit event. Response latency was near real time. The delay between a sensor event being detected and the dashboard updating was minimal throughout all testing, as you could clearly see in the demonstration. Communication stability was stable throughout. No data loss or interruptions were observed during continuous operation. System complexity was low. Compared to camera-based or machine learning approaches, LabFlow achieves reliable performance with significantly less hardware and no complex algorithms. The only limitation observed was in edge cases, when multiple individuals passes through simultaneously or when very rapid movements cause overlapping triggers. These scenarios are uncommon in typical laboratory environments. The system overall provides reliable real-time operation with minimal overhead, a practical, cost-effective solution for smart laboratory management. To summarize, LabFlow makes 5 key contributions. First, a low-cost IoT-based laboratory occupancy monitoring system with a real-world deployability using affordable off-the-shelf hardware. Second, a dual infrared sensor directional detection mechanism that reliably distinguishes entry from exit without cameras or complex sensors. Third, a lightweight MQTT communication framework that enables real-time scalable data delivery from the embedded device to any number of web clients. Fourth, a real-time web dashboard with color-coded threshold classification and live event logging, making laboratory availability instantly readable. And fifth, a modular three-layer architecture where each layer can be upgraded independently without affecting the rest of the system. Regarding future work, the current system has two main limitations: reduced accuracy in high-density simultaneous passage scenarios and the assumption of a single entry point. Planned future directions include expanding to multi-entrance environments, adding cloud-based storage for long-term usage analytics, and predictive modeling. applying machine learning for adaptive occupancy estimation and integrating with smart building systems. Thank you for watching.